work like that, but in a greedy algorithm, like a decision tree, once you've done the split, that is done. Of course, later in here, I'm going to say, okay, for the data points that go this way, now I'm acting only on the left side here. That's the left side. That's the left side, and this is the right side. Now in here, I'm going to say, pick some other feature to create a split. Say feature 2 and threshold 2. That's going to be a threshold somewhere here upon feature 2. And how is this split going to work? Like it's going to say out of this region here, it creates a visual region, that set of data points, and that set of data points. So this is going to create a L and L right. This is L. This is feature 2, smaller than the threshold, and feature 2 bigger than the threshold. So L here, smaller than the threshold means here. If this is from min to max. Okay? Nothing new so far, it's just the same thing we said last time in a more visual way. So decision trees, that's what they do. They chop off the data piece by piece. And those chopping offs are always parallel with the feature axis because every simple split again means it's based on a feature and a threshold, and if this is smaller than the threshold, it's the left side, bigger than the threshold is the right side. Those are simple splits. You can imagine not simple splits that depend, say, on two features, right? I could say if that feature is bigger and that feature is smaller and something, or Adam, or make a product of two features, I could have this much more complicated branching than just one feature with one threshold. But for simple splits, those splits will always look parallel with the axis, right? Because every split will be you either that side or that side within a certain region. So you can imagine what happens here, that if I keep building this tree down, every region gets split. Maybe this one will get split again, maybe, right, when I'm in this region here, I don't know what my decision tree, what feature is going to pick. Maybe it picks this feature, feature 2, with a threshold, but it could pick again feature 1, right? It's possible when I'm in this region to say, when I'm trying all features with all thresholds, say, okay, the next split is somewhere in here. Right? That could be. And then I'll have a region here. Maybe I split this one this way. And maybe that one I split again this way. And then this way, and then this way, and then here this way, this way. So you can get all kinds of small regions that accounts for the current leaves you have in the tree. Every time you split the leaf, you get 2 more regions. Now, what's that? Now, every region is independent of the other regions. That's a great advantage of a decision. When it looks at this region here, say how to split it, it has total independence to the other splits. It doesn't have to pay attention to the other data. In fact, it doesn't, right? Once I'm in this cell here, only the data that makes it to this cell is going to dictate what happens next. I'm not going to pay attention to the rest of the tree. So that allows me to say, when I'm in this region, if I'm unhappy with the current result, remember what happy means? When I decide not to split anymore, I have what? How do I say I'm happy here in something? I don't want to split no more. I have a very skewed set of labels, right? My vast majority of the labels are all red. Therefore, I don't need to split, right? That means I'm happy with the current majority. But every time I split, I'm only based on this region, so I can do something completely independent to the rest of the data. That's a great advantage because it doesn't assume a model. A lot of machine learning algorithms, say a naive Bayes algorithm, or a boosting algorithm, or a perfect machine algorithm, or regression, assume some sort of model about the data, and they're mostly correct. They tend to be correct, sometimes they're not. This one doesn't make any assumption. So if you have a, say, weird data set, or a data set that's have a lot of outliers, or something that's difficult, it's a good idea to try a decision tree first, even if you don't plan to use a decision tree as your main modeling algorithm, just to see what kind of splits it gives you. If you run a decision tree and within 2-3 splits you get a high consistency on all leaves, that means those 2-3 splits are probably what you want to use. You can also run Bayesian regression or Bayesian naive Bayes first, that we're going to study next to see what's going on. But decision trees have this ability of, even before you run your algorithm, they can tell you good things about the data right away. On the other hand, if you run a bunch of splits and you observe that you get stuck, like you can't make progress, even if you get pretty deep in the data, it probably means there's some complications there, the features are not correlated with the labels that well, for example. So decision trees have great visual abilities about data before we even talk about performance. Okay, so that's my point here. Decision trees, no model assumption. They also are quite intuitive. Visualize well. That is, if you don't complicate it too much. Any model, when it becomes very complex, becomes harder to visualize. That's true for decision trees too, right? It's one thing to visualize a tree with 2 splits, and another thing to visualize a tree with 200 splits. But nevertheless, they're more visualizable than other models, and have data explanations. Sometimes we don't know what's going on with a patient or with an image or with an email or with a set of emails. There's some problem that doesn't correspond to what we've seen in the past. Again, decision trees can explain that well. But they are hard to train. So let's say these are pluses, and this is minuses. So this is a big thing. This is work on any data. I can tell you that in my personal experience, when somebody gives me a new data set, that's for my consulting job. In industry, you have to make it work. Theory doesn't matter. Like, I'm great at explaining stuff. I can show slides. Nobody cares about that. Just make it work. The first thing I do, I always run a decision tree. Always. A decision tree and a naive Bayes code. Just to see what happens. That will tell me something about the data and will kind of give me some hint of what to do next. They're hard to train, as in long, because of this brute force approach. Remember, at every split, we try all features with all thresholds. On thresholds, we may be able to be a little smart about it, not try all the thresholds, but nothing we can do about features. So if my data set has 25,000 features, or something big, trying every feature every single time, that's going to take time, right? So they're hard to train, and they overfit. You got to be very careful. I'm not defining yet what overfit means in a formal sense, but you can, for now, this is saying memorize data without generalization. So the learning part in machine learning means I'm learning some sort of pattern or idea or concept that can be applied later, right? That's what learning means. If I memorize my training input with no ability to explain anything later except for that training input that I memorized, that's essentially a dictionary, right? I memorize everything I've seen, every single patient I've seen, and the disease it has and the symptoms it has. And I know that as a lookup table. If I ever see one of those patients again, I know exactly what they have because I have them in my table. But I have no ability to go to a new patient and make a prediction for that patient. Anything that I haven't seen exact in my training set, I cannot explain. I cannot make predict. I cannot do nothing. But I can do very well if somebody shows me the same exact patient I've seen in my training set because I memorized that, right? And since I memorize it, I can answer that verbatim, say, if the patient I have now matches one of the ones I've seen before, I know what the answer is. By the way, there are algorithms that work like that. Give me a new patient, they don't learn anything. Training means nothing. Training is easy because it doesn't do anything. Those algorithms work the following way. When a new patient comes in, I didn't learn anything. I got a new patient. I measured this patient against all the training patients that I've seen before, 1 million patients that I've seen before. And I'm saying, which ones of this big set of patients is similar to the current one? What are the most 3 or 4 or 5 similar patients with it? Maybe 10 patients, maybe 20 patients, however I want. Depends how big the data set is, right? I say, look at the most similar 10 patients, and if they all have diabetes, I'm going to say the new guy has diabetes too. I'm not going to learn any particular model of diabetes. I'm not modeling diabetes there. All I'm saying is this guy looks like these other 3. Whatever they have, he must have too. So training is no big deal in there. In fact, I don't do anything. The testing requires a similarity measurement between my new data point patient versus the old ones. So finding the 10 most similar patients in that case might require, if I have 1 million patients, I have to answer the question, which out of these 1 million are the 10 most similar? But you can see how that might be related to, say, how Google is doing, right? When you ask a query, the basic task Google has is to say, out of my 10 billion documents, which are the most similar or most related to the query, right? It's kind of the same question. Okay? So it's a ranking problem. So those methods are very interesting, by the way. Anybody knows what I'm talking about, how they call? Get the patient and then measure with everything I have, find the best 10.
K-nearest neighbor.
K-nearest neighbors. Lately, there's a lot of research into K-nearest neighbor for specific purposes. Justification, for example. Like if you are a lawyer and you do machine learning, you don't just want a prediction. You have to argue why you make that prediction. Well, because it was like a previous case from 1985 that did something. So you need to know how to argue those things. And also for ranking problem, K-nearest neighbors are back into play, and for other problems that I'm going to mention later. Anyway, my point in here is that decision trees are very different than KNNs, nearest neighbors, in that they learn a model of the data. This whole tree that builds up here is a model of the data. I'm expecting that the new patient passes to this tree, ends up in some leaf somewhere here, and in that leaf I make a majority prediction or a regression prediction on average if I have a regression problem. Everybody understood the regression variant? We speed it up last time. When you say a decision tree, if the quantity we want to predict is not a category or a tag, like spam versus not spam, instead it's a quantity, like a salary, or a price of a house, or distance to wherever you want to go, then the decision tree looks the same, but the criteria has to be quantitative in nature. Right? How do I split and what do I predict is based on an average and variance instead of information gains and entropy. Hands up, who figured that part out, like from the class yesterday?
I didn't understand, but I went to TA yesterday. He told me when we are for regression tree, we are calculating the least for constant square, we calculate the least mean square error. So that time, why we don't take the weighted calculation and then do? Because for entropy, you taught us that we take the weighted.
Yeah, I think it's still weighted, but if you do it for all points, it's weighted by default, because if you do it for all points across the split, you're counting the so many points on, no, if the split is uneven, right? I'm doing the quantity here as a label, so I'm measuring the variance of the mean square error. If I do across the whole level, that's weighted, right? Because if I have 1,000 points here and only 10 points here, 900 and 1,000 points contribute for here much more than the 10 points from here. So if I do it across all points, I'm effectively counting this side that has more points a lot more, right? But of course, you gotta weight it. I mean, there's no way to say, hey, all the points went, very skewed, and I'm just measuring something here, something there, I'm averaging by 2. But my question was, do we understand why it has to be variance and average? Or other criteria similar to that, and not entropy and categories. If what I'm predicting is a quantity, then the split has to be based on how consistent. The consistency notion is, it's still similar with before. I want everybody to have the same salary in this branch. I'm predicting a salary, right? So if they have very different salaries, I'm going to try to split into high salaries and low salaries, right? And they're consistent. In a quantity, we said consistency means what? If I have quantities, somebody else.
Low variance.
Low variance. So consistent. Low variance. So this is the label is the quantity, like salary or price. So if I have low variance, I choose, don't split anymore. If I have high variance, I'm going to try to make a split into high values and low values if I can. So my criteria, try all the features and thresholds, would be how do I get a better split of this into high values and low values. But then when I make predictions, I have this tree built up. New person comes in, I pass that person to the tree, I end up in this area here. How do I make a prediction? In the category world, it's going to be the majority, right? If I have so many reds and so many blues and so many greens, I'm going to say which ones are the most. It's mostly green, so I'm going to predict green in there. In here, I don't want to do that because those quantities don't work with a majority. I'm going to predict the average. And if the consistency work, if I have low variance in my leaf, the average is going to be very close to the actual values in there node. Okay, good. So that's what I have to say about decision trees. Now I want to move on, and I want to keep this picture in mind. So I'm not going to erase this picture. Okay? I want to move on to the next basic algorithm, which is the linear regression. So visually, what would we expect in these regions here to happen? I'm gonna erase some stuff a little bit and say, here's the first split, right? I'm gonna say this is a binary problem. Left, right? This problem was binary, so the labels are plus and minus. What would I expect if the decision tree says split it here? Take feature 1, pick this threshold, whatever's left side as a left branch, right? What do I expect for those pluses and minuses to look like? Like I have data points in here, right? These are my data points. All kind of points in here in this space. Sometimes this is called the data space or simplex, where all the data is in here. Everybody has a feature 1 and a feature 2. If those are houses, this might be the square footage, right? Square feet. And this might be the number of bedrooms. 2 features, one every house. And I have a bunch of houses here, right? What should I expect if the decision tree says split here?
Instead of being lost on one side and minus on the other side.
Mostly. Or at least better than random, right? If I have so many pluses and so many minuses in here, that looks like a nebula somehow overall, I expect a line to try to make a separation between pluses and minuses. Not perfect. I expect to say maybe there's mostly pluses here and some minuses, and mostly minuses here and some pluses. Right? That's what I expect. And then again, depending how stuff look like here, when I split further, I separate more the pluses and minuses. Now, decision tree is a hierarchical structure. It does some separation, and it's okay to have errors because you can do further separation and further separation in that area. Now, in linear regression, I'm going to look at this picture slightly differently. I'm going to say, let's plot the same data set and say, here's my feature 1 and feature 2. Feature 1, feature 2. And here's my label. This is easier to think of labels as quantities for now, and later on we're going to see if they're not quantities, if they're like binary plus minus or categories, what do we do? But for initial linear regression, let's think of this label as quantities, like prices and salaries. Again, we're going to modify this to make it work for all cases, but just for the concept. In here, I have the same points, right? And everybody has, we're gonna call this y, right? Everybody has a quantity associated with it. So this house here has a price, this house here has another price, another price, another price, so on and so forth. So what we're trying to get is a correlation between features and labels. Those are features. X is going to be the feature matrix like before, Y is labels. And not just that, linear regression makes a very strong assumption about the data as opposed to decision trees. It says this correlation is linear. That's an assumption. That there is a correlation. In fact, if we have to make an assumption that there's a correlation, like in all machine learning, if there is no correlation, there's nothing we can do. There's no learning in there. There has to be some correlation or handle. Features have to provide a handle for us to get to the right predictions. But the handle doesn't have to be a linear handle, right? It could be any sort of. In fact, everything that decision trees produces, if it's like this, then that, if like that, then that, and if like that, then that, tends to be not linear. In a decision tree, if you pay attention to how the splits are, you know, like we said, here's another split, and here's another split, and here's another split. Those splits don't make up for a linear correlation of features and data, usually. In fact, I don't know if you've seen this, to get a linear correlation with a decision tree, you have to do a lot of splits and end up with something like this, like a stair. That looks like a line, but in fact it's a lot of splits to the left, right. The stair would be many splits that overall look like a line. So it's kind of hard to match a line with a decision tree and the other way. They're very different algorithms. Back to here. What would I like is to say, well, the labels depend somehow on feature 1 and feature 2. Of course, in practice, I'll have more than 2 features. I may have 50 features in the span-based data set, or thousands of features. And if it's linear, visually, linear means there is some sort of hyperplane, right? There's some sort of, here's my regression plane. Surface. And what this surface means is that if you pick the proper feature 1 and feature 2, right, this is the coordinates. The coordinates are here, x1 and x2. This is the data point. When I pass it, I raise this up all the way to the plane. Wherever it intersects the plane, that is the corresponding y, the label. Right? That's how affine or linear surfaces work in geometry. So I'm looking for some sort of linear function that says y is approximatively, because I'm trying to match there. Not everyone might have their label matched by this hyperplane. Y might be, say, W1 times feature 1 plus W2. That's a linear function. And if I add a bias, I say everybody can get this hyperplane doesn't have to pass to origin, right? wherever this hyperplane intersects here versus the origin, that's called a bias. If the hyperplane doesn't pass through it. If I leave it like this, it passes through origin, right? It's 0, 0, I must get the 0. But if I add a W0 times 1, this is the bias term. I don't want to worry about algebra right now. I'm going to worry about in 20 minutes. I want to worry about geometry right now. Everybody have seen those lines or hyperplanes in 2 dimensions and 3 dimensions, and understand that in any linear surface in geometry, it corresponds to a linear equation, right? A hyperplane in 3D is governed by the linear combination of the 3 coordinates have to equal 0. A line in 2D, so this is a 3D plot. If I only have one feature, right, say I have the square footage of the house, that's feature, versus the price, that's that. How is this going to look like? My regression is just a line. It's only one feature as opposed to 2 features. And what I'm trying to correlate is I expect bigger square footage of the house to correspond to a bigger price. Typically, bigger houses cost more money, everything else being the same, right? So what I expect is that as the square footage increases, the price will increase too. But of course, not everything will be on the line, right? There'll be around that line, maybe every once in a while you get an outlier. Here's a house that is not so small, but it's next to a lake, so it's a lot more money. We get to see something like this. It's not on the line, but the regression makes the assumptions on the line. So we're going to say, okay, what's the best line that kind of approximates that? Even though we know the houses are not expected to be all on that line. We're not trying to match with this line a particular dot or to pass through many dots. We're kind of trying to be in the middle of everyone so that our assumption that this is linear, it's roughly satisfied. Roughly means we're going to get some errors, right? Because very few points are actually on the line, and that doesn't matter. Whether the point is exactly on this line or not, meaning the feature and the label correspond exactly, that doesn't matter. What matters is, on average, how far away from the line we are. Because this looks like a line, right, roughly, as opposed to something that will be all kinds of points here. Imagine if I have something like this. Here's my square footage. Here's my price. And it doesn't look like a line at all. For some reason, the houses look like that. It's kind of hard to put a line here, even if I allow my regression to go backwards, to go anti-correlated with the data. Maybe for some reason, larger houses cost less money because we are in, say, depression and nobody wants to build a large house anymore. If my data looks weird, there's no way to pass a line that doesn't have big errors. No matter how I put my line, say I put my line this way, some points are going to be very far away from the line. I put my line this way, again, some points are going to be far away from the line. I put my line this way, some points will be far away from the line. The problem here is not that I don't know how to find the best line. I know how to find the best line. Problem is, those houses don't have a linear correlation with the price. There is no good line in here. Hands up, who's with me? Yes. Good. This is a critical point in all machine learning, and especially in industry. If you go in industry, that's what I do for consulting, you know. Your problem's not going to be that you don't know how to find the best line, or you don't know how to download the package that finds the best line for you. Because that's easy. Everybody knows how to do that. And if you don't like lines, you get quadratic functions or, you know, support vector machines, fancy stuff, neural networks, right? That's easy to install TensorFlow and run it. I mean, it's gonna take you a few days to figure out how to do it, but it's not rocket science. You know, rocket science is to engineer TensorFlow internally, but that's not what you expect to do in industry. The problem in what you're gonna have if you only stick with basic machine learning and you work in this field is why my lines never feed the data. Right? It's the model assumption that's broken here, that my data is linear, that's my assumption, and in fact it's not. So I have to work on that assumption. No matter how hard I try to find this line, try different regression algorithms, different objectives, different numerical methods, and so on and so forth, I'm going to fail because there's no good line that fits. I'm never going to have this problem with the decision tree. That's why I like so much decision trees personally, when I don't know anything about the data. It could be anything, right? Decision trees can work and explain the data and even produce a good model sometimes without making assumptions. So even if the data is weird, the decision tree will still do the best it can. In here, if I run regression and I look at the performance, I'm not going to know if I don't get a good performance, why that is. Of course, in practice, regression has many, many advantages. Not that it's fast, but if you have a lot of features, here's a question for the smartest people in the room for the next time, for Thursday. Why is it that this assumption will be satisfied if I have enough features? So in here I have one feature versus the price, right? In here I have two features versus the price. On these examples, you can see that if I draw a line, it's quite strict to require data fits this line. You can imagine many ways in which data doesn't fit the line. Now I'm saying the other extreme. Suppose I have 20,000 features for, say, text, right? When we extract features from text documents, features are based on words. There are many, many words in the English vocabulary, right? Up to 200,000 basic words, and then 500,000 if you include all the words that nobody knows, right? It's 500,000 features. So now I have 500,000 features. They're very rare. Every particular interesting word, like Virgil or Northeastern name, appears in very few documents. They're not words that appear in every single document. So most of the feature values for words would be zeros for documents. In that data set, I say, lines will fit. No matter what the documents are. Like any text emails or tweets or web pages or books, whatever. If I have that many features, 500,000 words, and they're rather sparse, the one that matters, because the word like the don't matter, right? We're not going to count on word like the or of or about as features, or only words that mean something that's going to count as features. Why it is that in that case, the regression assumption that a linear model on these 500,000 features fits the data labels. Any data labels, say you want to categorize those books or tweets or emails into whatever categories, doesn't matter what they are. The assumption is satisfied. That's not an easy question. But if I have enough features, I'm going to satisfy that assumption. We get to those data sets a little later. Those data sets are a little particular text data sets. For the data sets we have now, we don't have those problems. The span-based data set, it's based on text, but the features are not based on words. There's only how many features? 50 features in there? Obviously, those are not the words in the span, because they'd be too few, right? So, the problem with regression is satisfying this assumption. Now, how do we get a model? So we just say, this is what we want. We want to match the labels based on the features we have. This is a feature, this is another feature. So what is our model? Consists of what? In here, the model is the splits, right? Which feature to split and when. What is the model in here?
It's your way out again.
The W's, right? W0, W1, up to W. I think I'm going to have DWs. If there's D features, DW. Now, I tend to write the feature exponents at the top as indices, and the down would be the data point index. Data 1, data 2, data 3, like image 1, image 2, image 3. You don't have to follow my notation. Different books, they use different notations, but you have to be consistent. If you don't like to write x11, that say x21. This is data point 2, feature 1 for me. You can write x21 this way if you want, or even x12 backwards. That'll be hard to read. But you have to be consistent. You can't say on one page is that way, on the other page is the other way. So pick a way to differentiate those things and stick with that. So that's what I'm trying to get here, right? This is my model. Regression, when it's done, is going to produce a bunch of numbers, coefficients. And that's my model that I'm going to use for predictions later. Now, this is a very large class of machine learning models. They make an assumption. They say data satisfies the following property. Of course, the data doesn't. Not all these points are on a line. Even when it looks like they are mostly, it's unreasonable to expect all the points to be on a line, right? And then those models say, given the assumption I made, what are the best W's? Those modeling models, modeling assumptions, they know this is not going to be perfect. Right? There is no W's that puts all the points to a line. But then I'm asking, what are the best W's that gives me the smallest error? Right? So we need to find a way to measure error here. The standard way to measure error, let me draw one of these pictures better. So how do I measure error? I have here the regression line. And here is the data point feature X. And this data point has, say, I'm going to say in a regression sense, this here is f of x. This is where the regression line, let's call it, I think, h, but let's call it the note h. For this x now, it's multiple features. So I'm putting in this plate here, or in this space, all the features that I have, not just one feature. It's x1, x2, x3, whatever it is. So now h of x is the prediction, or the model says that if x is here, this is the blood pressure, age, and whatever symptoms I have about the patient, the quantity you get is h of x. But the reality, y, is here, the label. So that's kind of my error, right? Is like how my model assumption is that those points will be on the line. When they are on the line, maybe this guy is exactly on the line, error is 0, right? It's exactly on the line. When it's not on the line, I've got the distance from where the line is to where the actual y is. This is the true y. Again, I want to think of this in terms of quantities for now. So the true y's, even if I say patient, that's a mistake. I don't want to say patient. I want to say salary or a price, predicting quantities. So this error, we have a standard way of measuring it. Somebody said the error should be what? Some smart person figured out that the error should be y minus
Square.
square. Y squared.
It's easy to do negative, positive. If it's negative or minus.
One thing is, it goes back and forth with positive and negative. I don't have to worry it's that way or that way. If I would have to worry, then some positive errors will cancel negative errors. I may be the impression that everything works out when in fact everything is far away from the line. That's a good point. The differentiation, okay, what else?
It also makes it better to be 1 off all the time than randomly 1/5 of the time be 5 off. So we're always being consistently close.
So what you're saying is because of the square here. I think what you're saying is, let's look at two different situations. I'm not sure I understand what you said, but let me try to work it out and you tell me if it's correct. He's saying, hey, what if I have this situation, 4 points on the line and 1 really far away? Versus the same line here, no, a bigger line, say cross, actually let's put it in the same one. So here's line number 1, regression 1 line. I can choose a different line that says, well, this one, in terms of exact matching, this one, everything is far off the line, right? All 5 points are far away. This one has a little distance here, little distance here, little distance here. All those are errors, right? And this one has this error. So I think his point is, which one of those two lines is better? The one that has errors everywhere, but there is small error, small error, small error, small error, and some error. Or the one that matches those 4 exact and has a bigger error here. Is that the point?
Yeah.
Well, that has exactly to do with the square. That notion. Do you want to be close to those 4, but then get a bigger error here? Or do you think it's better to go allow errors on those 4 because this error would minimize? I mean, you can say it's a matter of preference here or some other, whoever runs the machine learning algorithm has a purpose in mind, right? But the square will favor which line? R2. What if I put a 4th? Or a 6th or a 10th? The more I put a higher exponent, the more bigger errors will dominate, right? One big error would overwhelm a lot of small errors. So the higher this exponent is in here, it says we don't want big errors. We can tolerate small errors, but big errors are going to overwhelm the small ones. That goes the other way too. The smaller this exponent is, the more we like fewer errors, even if they're big. We can tolerate bigger errors if they're not that many.
Do people in practice change that exponent?
There are losses that, not randomly, but there are losses with exponent 1. You have to take the absolute value in that case to deal with the positive negative side. But yes, you can do the I think 1 and 2 are the popular classes. Now, of course, 2 has very important differentiable properties. It's very nice. What other properties it has?
Doesn't it match up with maximum likelihood solution?
Right. It matches with a lot of statistical and information properties. What else? The 2 we like so much. It has so many names. This error function here has many names. Regression loss, square loss, root mean square loss. You call it. This is the loss, the first loss everybody knows. But I'm looking for a particular property. This 2. Quadratic, right? It's a 2. I'm looking for a property that has to do with the yes.
The linear algebra solution for linear regression?
There is a linear algebra solution. We're going to see it today, actually. So, but to get to that comment, we have to see a solution of what? I mean, he went too far. What is it that we're trying a solution to get for? There is a solution, like you say, exact solution.
It's a convex one.
Is what? Convex. That's the one. I like convex function. In fact, everybody in machine learning likes convex functions. There is something to do with how are we going to get the solution to the problem of what are we trying to do here? We're looking for lines, right? We already said we have a strong assumption. Linear means we're always going to get lines no matter what we do, right? That's what we want, lines. But it's up to us what line to get. So which line are we going to get? Or are we trying to get?
That minimizes the error.
Minimizes the error. Now, of course, the error, we said we have some options to define it. If you don't like 2, you can put a 3 or 1 here. There are many ways to define this error, right? But whatever error it is, we also call it objective or loss or cost. For some reason, people can't agree on names, so there's a whole dictionary here for what this function is. All of them mean the same thing. Okay, loss, objective, cost, error. That's the one that we're trying to minimize, right? So there is now a procedure that's half mathematics, half computer science. I've got my error, I got my loss, my cost. This is what I'm trying. This is the best line is the one that minimizes this thing. Now, I know what a line is. A line is defined by a bunch of W's, the numbers. It has to be. The question, the procedural question is, how do you get the W's that minimize this error? Meaning, how do you get the best line? How do you minimize it? This is a very typical pipeline in machine learning. I'm defining a model with a strong assumption, Gaussian, right? It fits a particular distribution. I hope you remember what Gaussian is, but even if you don't, this is one of the things I'm counting on. You go home, you check it up, checks out quickly, Gaussian. I'd say it has to be a Gaussian distribution, or close to it. Then Gaussian has a bunch of parameters, right? Not W's, what Gaussian's functions have.
Variance, mean, standard deviation.
mean and variance, right? Mean and sigma. So then I'm going to ask the same question. What is the mean and sigma such that my model is as close as possible to the data? It's a very typical pipeline in machine learning. And people can define a lot of models, aka Gaussian, linear, quadratic, so on and so forth, and a lot of objectives. What does it mean for a model to be good? But then it comes down to this last part of, okay, now that you define the model, it's linear here, and I define the objective, is that function there, how do you get the best W's, the ones that minimize the error? So a typical machine learning pipeline is to create a model assumption on parameters. For regression, the parameters are those W's, right? So if this is linear, the parameters are going to be W0, W1, so on and so forth, WD. If this is Gaussian, this is going to be the mu and sigma matrix, for example. Right? I create some sort of model. I say my data has to match that model, or I think it matches that. And then I define a loss or criteria. That's another name here, criteria. And then I say, okay, find the parameters that minimize or maximize, depending how it's set up. Some functions we want to maximize, other we want to minimize. This one obviously it's an error, we want to minimize it. And maximize the loss. This is a very typical pipeline. I create some sort of, here's what I think the data looks like, has to have those parameters in it. Neural networks are like that, right? In a neural network, what are the parameters? Yes.
The weights.
So network weights. There could be a lot of them, right? In a neural network, you get matrices and matrices of weights, a few layers of weights, right? But nevertheless, the whole network is defined by those weights. We're going to get there. We don't have to know what a neural network is. It's just something with a lot more weights than regression. Then we have a loss at the top of the network. Many neural networks have different losses depending what the problem is. It could be ranking, it could be binary, it could be multi-class, it could be all kinds of losses, right? Once I define the loss, that's typically related to the task. The loss has to be a mathematical translation from the domain expert, the doctor, the lawyer, into the math. So it's very hard for mathematicians to define a loss alone. They have to map to what is it that you're trying to achieve, sort of thing, into the math. But once you have those things, I'm down to pure engineering. How do you find the parameters that minimize that loss? This is a lot of math in this part here, but it's also a matter of implementation. Even if you know the math, how do you actually write the computer program that does it? So for a long time, people have been concerned about this, and there's entire subfields of mathematics dedicated to this. This is typically called optimization. Where we take a model and we take a loss or criteria and say, okay, how do we find the best parameters to fit that loss? And this is where convexity makes a big difference. Convex losses or criteria are much easier to optimize than random ones. Now, the basic optimization that everybody knows is brute force, right? Try all the possible parameters, measure the loss of every single one of them, and remember which one was the best one, and use that one, right? I mean, that's a very simple thing. If I try all possible sets of parameters, I'm going to know eventually which one is the best one, because for every one of them I measure the error and I keep track of the smallest error, and at the very end, that may be hundreds of years later, I may know which set works. Is that what the decision tree does? Is it trying all the parameters possible and in the end decides that set was the best one? What are the set of parameters in the decision tree, although we have no model? Overall, if I have
Threshold.
all the features and all the thresholds together, right? Feature 1, threshold 1, feature 2, threshold 2, the branch, feature 3, threshold 3, so on and so forth. Did the decision tree try all possibilities?
Yes.
That would be a global optimization. Try literally all possibilities of features and threshold. What did the decision tree do?
Local alignment.
Which is greedy, right? A decision tree makes a what's the best I can do right now. Once I made that decision, I don't go back and change it. There are variants of decision trees who go back and change it based on, say, some dynamic programming sort of methodology. But they much more complicated than the simple ones. So a decision tree is trying to attempt to do the same, try all possibilities and see which features and thresholds work the best, without a modeling assumption. The best is the consistency. I mean, we have a criteria, it's split, but that is the consistency in the labels. What I say, it's not a loss. The reason I say that's not a loss is that that's not an assumption about data. It's just the purpose of classification to get consistent labels when I'm done splitting. So that's a greedy algorithm. That is not a global optimization. In here, we may have the same problem quite a few times, especially for neural networks. We cannot guarantee a global optimization. At the end of the procedure, the engineering procedure, we're not gonna know we have the best possible parameters. We're gonna say, we have a set of parameters that we think they're good, in the sense of if you try to move them a little bit, you don't improve. But there might be some other set of parameters that we didn't try, and they're actually much better. A lot of these optimization problems end up in this unknown state. I've got something, I think it works, but I have no clue if there's a better set of parameters better than what I have. For some problems, especially the complex problems, we can guarantee that the set of parameters that we get are the best possible. So we don't have to worry that I stopped the optimization before I got the best result. So that's why convexity is a big deal. Okay, so then how do we do it? This last part here. We pick a loss, we're gonna use this one as a standard regression loss. And our model assumption is that it's a line, so we have those coefficients. So what do I have to do to compute these W's, right? So let me write this a little bit more formal mathematically. I'm gonna leave this, I guess we may not need this picture anymore, we have it there. Before I do this, would it make sense to measure distance differently? To say, if this is my point here, so what did I say? I have a x feature point. This is here, x feature point. This is the y. This is the where it intersects the plane. Right? So this is in here, h of x, and this is the true y. This distance is kind of parallel with the y-axis, right? It's the difference or where this line intersects the plane versus where the true label is. But in geometry, sometimes people take the distance perpendicular. Say, here's the true point. How far away is from the plane? Well, it has a distance to the plane that's not this line down perpendicular on this surface down, but rather this distance. Now, if the point would be on the plane, both distances would be 0, right? If this true y happens to be in the plane, there's no distance here, that's 0, and there's no distance here, that's 0 too. So in that case, for points exactly on the plane, for whoever likes it better at in here, instead of measuring this distance, it will be the perpendicular, which is this distance that I'm measuring. That's a different loss by measuring distance this way. Geometrically, how far those points are to the line or to the plane is this side. It's the distance from the point to the plane is the perpendicular, right? This will be much harder to work with. It's another thing that you can, beyond the homework and the basic material is, what if I want the geometrical distance? How would I how would that change my whole regression derivation? Okay, so what do we have? H of x. So first of all, we have an x data matrix here. Here's x. X 1, 1, up to x 1, 3, x 1, 1, or up to x and e. We have a label vector y1, yn. And we have h of x is, so for xi, that will be the sum of that is the regression function. And the error or loss, I'm going to call it J. J is a function of, we'll see in a second, this is a regression that's based on the W coefficients. So W as a vector is W0, W1, WB. So this HF here, XP is which is the sum for all data points of sum of So this loss is a function of W's, right? If I have a bunch of W's coefficients, regression coefficients, that's their error. Is how far away the squared losses. The squared losses are these points in here. Now that's for each data point. So this sum here is the regression dot product of the sum. It multiplies, takes a data point, all the feature values, multiplies the W's, gets the, this is the prediction, and this is the true label. Yes?
For the dimensions to work out, you just add a column called 1s
Yeah.
on the left of the x.
That's correct. So we can add a column 0 here, which is all 1. Because who's going to be W0 multiplying with? There is no X0 feature, right? You got to be careful how you do this when you implement your code. If you start counting features at 0, that's okay, but you need to add a column of 1 that creates a bias. This 1 will add up the W0 to every single one of those summations to create a bias there. Again, geometrically, that will correspond to the line or the plane, not necessarily passing to the origin. Right? If I want to pass to the origin, the bias is 0. But if I want this line, maybe the line I'm looking for is a line like this. To make it not pass to the origin, I need to add a bias. The bias is W0. And it multiplies with a 1. So what people do, they add a 1 to the column. One column to the data, and then the coefficient for that column is the bias. You can try without the bias. Just then you restrict all the regressions to pass to the origin point. Because if you don't have the bias column, 0 will correspond to 0 necessarily. Okay. So we want to minimize this thing, right? As a function of the coefficients. So just to recap, who's who in here? YTs are they given to me? Yes, that's a training set, right? So those are given. XTs are the XTDs, feature values. This is the Tth data point D feature, right? If it's 0, that's a 1, it's the first one column I have. Who's the W's? Those are regression coefficients. How many regression coefficients are here? D plus 1, right? There's D, 1 per feature, plus the bias W. So now, who's known or given or fixed in here? X and Y's are fixed, right? In the training set. So the variables or the unknowns, what I'm trying to get at here are the W's. So how do I minimize the function? Take derivatives and
Equal to 0.
all right. So how do we do that? I'm going to say here's a so to minimize the loss, differentiate of the loss have to be approximately 0. I'm saying this informally. That's a way to set it up. We say the differential of that loss have to be 0. Now, before I go there, just a quick high school recap. Why is that? Why is it that when I'm minimizing a function, I'm looking for where the differential is 0? Intuitive explanation. Somebody else. Yes.
Because at the minima, the differential is 0 for any equation.
Yeah, but why? I mean, that's what I'm asking. Why is the differential 0 at the minimum?
That's why it's not.
Minimum, which means the peak or the
Right, so how the minimum looks like? Minimum looks like something coming down and back up, right? That's the minimum. And the differential geometrically corresponds to the slope or tangent. So if this is really a minimum, the tangent has to be flat. Flat means 0. How about maximum? If I have a function that has a maximum, isn't that true that the maximum has also 0? By the same principle, the tangent or the slope is flat, therefore 0. So if I differentiate, I set to 0, may I get the maximum instead?
No, we have to again differentiate.
For this is.
Find out whether it's maximum.
Say again, louder.
We have to again differentiate it to find out whether it's a maximum or minimum. And it will depend upon the slope.
That's true in some cases. If I set the differential, so first of all, I want to go to conceptual high school. If I differentiate the function that has a minimum and a maximum, both of them will be 0, right? So it's clear that one of them is a minimum, one is a maximum, if I know that, right? Now, what he's saying is that you have to do additional steps. I wouldn't go in saying what those steps are, like second differential, so on and so forth, to figure out where you are. There are other versions of that, how to figure out where you are. But I want to concretely for this problem. This is my loss, right? This one here. If I differentiate it to 0, can I get into the maximum? Somebody else. Why not?
It's a convex.
If this is a convex function, it looks like this, right? Maximums, even though they might be limited, not infinity, because of the space range, it might end somewhere. There's no differential in there if it's limited, right? In a convex function, if you get the 0, it's the minimum, 0 differential, minimum, and it's a global minimum. That's a nice thing. If a function is convex, it can only have a minimum. If it's not convex, it may be something like this, right? And then it has multiple minimums. Yes?
We'll summate the loss over all the data points. Is it still convex?
That's a good question. He's saying, hey, if you show me this versus, just one data point, I believe you that's a convex function. But you're summing up over, this is errors for each data point, sum up over all the data points. Is it still convex in a W, right? Because this function I have here is a function of the W parameters, right? That's what it is. X and Y's are fixed again. So his question is a very good one. This is a quadratic function, obviously convex. If I wouldn't have this main summation over the data points. So these are the data points. and these are the features. Right? Is it still a convex function in W as a summation? That's a pure mathematical question. Right? Because at this point, this is pure math. I have a function, I'm talking about convexity, nothing to do with machine learning, computer science, nothing like that. If I sum up this function, do I get a convex over, T might be 300,000 data points. So for people good at math, why don't you try to figure out this by Thursday? Is this a convex function or not? That has, by the way, important implications into the machine learning. If it's convex, again, what do I get? The minimum that I'm going to get by differential is guaranteed to be the global minimum. Right? Once I get the minimum, I don't have to worry about nothing. If it's not convex, I may get this minimum or this maximum. What the differential equals 0 might give me all those points where the function is flat. So then I need some other techniques to figure out, okay, are you in a minimum, are you in a maximum? Is there a better minimum than the one you found? If you can find all of them, that would be easy to check which one is the one you want. This is a major, major problem machine learning. Most machine learning fancy systems, they have these amazing loss functions that show they're natural to the problem and all that. They have the model assumption. They show that that works with user studies. Impossible to find the parameters. Literally impossible. So the most fancy machine learning setups have this problem that the model works great, the assumptions. The loss, it's exactly set up for the task, say like a ranking loss. It's not possible mathematically. Nobody knows how to do this other than brute force. Try all the possible parameters, see which one works. But that's infeasible if I have many features, many complicated model and many data points, right? You can't try all possible. So I'm aware of quite a few models, at least 3 or 4, that we have one in research that if we could optimize it, if we could solve this last step, in 2016, very good paper submitted to a famous machine learning conference. If we could do this properly, that would be a breakthrough. And many people in machine learning are at this stage. I have a very good model assumption, I have a very good loss, but I have no way to optimize for the parameters. In fact, a lot of the mathematical side of the machine learning right now is concerned with these steps, better approximations. No one's trying to find the best possible parameters. But when you hear about new optimization for the EM algorithm, for example, what they are trying is to at least guarantee that you don't get a very bad minimum. To get a minimum here with certain techniques. It's not the best one, but it's not something very bad. So that's a problem for many machine learning algorithms, how to do this optimization. There is one very famous paper that was a very prestigious award in, I think, 2011, that the guy, Carnegie Mellon, they say, we know this will work very well, and we know we can solve this, so I'm only going to show you the results for data sets that have 35 points, because that's the best we can do, 35 points. Right? You can imagine that's not related to anything that works in industry, right? Everybody who can only do 35 points with their optimization method is out of business. But there are quite a few tracks stuck into that optimization, right? Now back to us, assuming we can solve this problem by Thursday, convexity over the summation or not. Let's assume it's convex, huh? Even with the summation. We're going to take derivative, set it to 0. So then what's the derivative? I'm going to write this a little bit different. I'm going to say that I'm going to add a 1/2 in front of it. That's not going to change anything, right? Because 1/2 of it is still equally good. Why do I add a half? Differential would work better with a half. And I'm going to say here this is in matrix form xw minus y transpose times xw minus 1. So keep in mind that y is a vector, x is a matrix of size. I'm going to say n by d, although it's really n by d plus 1, because I added this column here, right, the 1 column. And the W, how this needs to work is n by d. This has to be what kind of dimensionality for the product? D by 1, right? So W is, I need W to be not this one. I need to be W0, W1, WD, right? D by 1. So I need something like n times D times 1. This is what? For the minus to work. These are all matrices, right? So we n by 1, and this one same here. The result will be of this operation, n by 1. When I transpose it, will be 1 by n, and this will be n by 1. So this transpose is what? 1 by n times n by 1. This whole thing will be 1 by 1. So this whole fancy matrix vectors and all that, in the end, gives me one number. That's from here, right? You can see that in here, this calculation in the end gives one real number. Even though I write it with matrices, I get one number. That's another thing that needs to be ironed out today. If you're not familiar with matrices, multiplications, and dimensions and how they work, you've got to do that very, very quick. That's very simple, but it's okay to not remember. You know, I've done matrices 6 years ago. Since then, I haven't done anything with them. How do they actually work? Okay, that's fine. But by the end, by Thursday, definitely you have to know how matrices work. So now let's take differentials. I'm going to leave this picture here and erase. Let's differentiate this thing right here. So I'm going to say this is my differential operator. And so the differential is with respect to the differential with respect to W. Now W is a vector. So I'm going to start writing the differentials, and we have to see if we agree that that works out the way I'm writing it here. The differential with respect to W of my function, g of W, which is this function here, is the differential with respect to W of 1/2 xW minus y transpose xW minus 1, right? That W from there? Hands up who's with me so far. Hands up so I can see them, please. Okay, this is a good moment to ask a question. If we, the notes are, of course, online, so you can check them out. And I'm going to make some clarifications later on about what actually matters here for the class, for you, for the homework, and for being over machine learning after the first class. There's a very different story if you want to be a machine learning PhD student. But some of you will just take the machine learning class and expect to work, be able to work in data science, what matters. For now, I just copy this from here to here, right? From here, that's the one there. So what is that? That is this 1/2 in the front, differential with respect to W of, when we open up some parentheses, W transpose X transpose X W minus W transpose X transpose Y minus Y transpose X W plus Y transpose Y. How did that happen? Where is this stuff coming from? So where is this coming from here? W transpose X transpose X W. Is this stuff transposed times this? It's kind of opening parentheses here. Where is W transpose X transpose Y coming from? W transpose X, XW transpose, that's W transpose X transpose times this Y. How about Y transpose XW? Y transpose XW. And Y transpose Y? Y transpose Y. So what is this transpose doing? That T there, what does it do? So if I have a matrix, 1, 3, 9, 5, transpose, what do I get?
It's 9.
And if I multiply A, B, transpose, what do I get? Very good. And if I have A minus B transpose? Is that a question or? By the way, I'm not that good at math. Honestly, I'm not kidding. I'm not good at math. Everything I say on the board, you have to verify. Because sometimes I may be sneaky and say things that are not true, just to see if you verify it. So I would go home and try to see if this is actually true. And by the way, when I say something like this, I mean in general for any A and B matrices. It's not for a particular one. If it would be a particular, I would say, if A is that particular kind, then it has this property. If I say this means for any matrix. So don't blame me if this stuff is wrong, because your job is to go home and verify it. Okay? So now, where are we going with this? We have some holes here. 1/2. So let me check I have this right. W X transpose here, X W. W transpose is transpose 1. Okay. So how did I get here? This is the same as this in here. W transpose X transpose Y is in here. Y transpose Y is in here. And I replaced Y transpose X W with Y transpose X W Y. X transpose W Y. So this is where stuff happened. But how did that work? Why is that same as that? Maybe my notes are wrong.
It's taking the transpose of the whole.
Yes.
Oh, right, so that if you transpose, if it's a sum of things, it becomes.
Yeah, but I didn't transpose everything. That would be true if I transpose everything.
Sure, but that whole sum is going to have to be that scalar, so if you take it.
This whole thing or just this term?
They all have to be the sum to the scalar. So then you can transpose them however you want, because you're transposing scalar.
Right, so his argument for this is that this thing is here as a scalar. The dimension is 1 by 1. Is that true?
Yeah.
Is that true? Is this a 1 by 1 thing?
Yeah.
If it's a 1 by 1 thing, when I transpose this, transposing a 1 by 1, it's itself, right? Right? And then that's what I did. When I transpose, how do I transpose a product of 3 things? With W, they reverse the order, right? W, this one last is transposed, then the X is transposed, and the Y transpose. That's another thing that we need here. If I take the y, transpose it, and transpose it again, I get y. And the reason the transpose doesn't change things, according to this explanation, is that this is a scalar 1 by 1. So then when you transpose it, you get the same thing. Okay, let me keep going. That is, of course, W transpose X transpose X W minus 2 W transpose X transpose Y plus Y transpose Y. Now, what's up with the differentials? Differentials, if I differentiate with respect to W, two functions, a summation. Can I take the differential separately? Can I say that's the differential of the first function plus the differential with respect to the same argument of the second function? Yes. That's the kind of same day, check it out, make sure it works. If you're not familiar with this differential, gotta be solved today. Okay. So if I break this, what's gonna happen to the differential of the last term? Why? Last term does not depend on W. So conceptually, the differential is the change in the argument. If there's no W here, there is no change, right? So the differential with respect to W on something that does not depend on W, that's it, no change. So let's write that down. That's the differential of W T X transpose X W minus 2 W transpose X Y. And I'm going to say here, this is 1/2 of, actually let's break them easier to follow. That is the differential of this minus 1/2 differential of 2 W transpose X Y. The other one I'm not going to write because it's 0, we just said that. So this in here, I say, I'm copying from the notes. Let's see. This is 1/2 times 2 X transpose X W. That is this guy. And this in here is minus 1/2 X transpose Y times a 2. There is a 2 in there.
So I think I'm just having a little trouble with the notation. When you made us change a couple step back, you said that Y was a scalar. Where did we say that Y was a scalar in this process? And then our
Y, you say Y?
Yep.
Y is a vector.
Y is a vector. Okay.
Y is a vector, 1 by n. W is a vector, but when you multiply 1 by n times n by 1, you get a scalar, right? Because the product, when you multiply things, the internal dimensions don't matter at the end. It's just what you have at the extreme. So you can multiply vectors. His argument, I think somewhere here, is that if you look at this, when you multiply this, the dimensions 1 by 1. So that one when you transpose this. But what's going on in here? In here, I'm going to say, do we remember how a differential works for not a vector but a scalar? Right? If I try to differentiate, now W is a scalar here. W times anything. What do I get? A, right? So isn't that what happened here? W times anything the differential ended up being that something 2x transpose y?
But it's W transpose and not W.
Right, right. So that's before, because for vectors, there's a transpose. There's a transpose here, but in scalars, transpose doesn't matter.
So in vector also, what I'm trying to understand is if it's a vector, we do not consider if it's a transpose or not a transpose. It will
No,
be
for
the same.
vectors will make a difference. For scalars will not be a difference whether transpose or not, but for vectors will make a difference. So I look at my notes and I'm like, damn, why this works? Like, I know it works like that. Okay, I know it works like that for scalars. And I hope you guys know too. If W is a scalar, multiplies with something, take the differential, you get that something, right? Mechanically, that's what happened here. Mechanically. How about this one? What's the analogy in unidimensional for this one? The differential of this stuff here would be what? The differential of, if this is a scalar, would be W squared times something, doesn't matter what the something is, A. What's the differential of that? 2WA, right? Is that what happened here? There's a 2, and then there's a W left, and then there is whatever was inside? Of course, this has to be, to match it there, has to be the transpose times the A times W. For scalars, doesn't matter, right? This is still W squared in here. Whether it's transpose or not, it's W squared. Hands up, is with me? So what did I achieve? I applied the mechanics of scalars differentials to vectors.
So in the second equation we can have 2 W transpose A.
In here?
Yep.
Yeah, I got a 2 here too, right?
Instead of W, we can replace W with W transpose
Right. In here, it's for scalars, won't matter, right?
for the output. Yeah, but
I can have here W transpose. Yeah, because for scalars, W transpose is the same thing. But for vectors, it's not. For vectors, there's the transpose thing. Okay. So here's what we're gonna do. We have an answer. This is easy to compute now, right? What is this? X transpose XW minus X transpose Y, right? Did you guys swallow the mechanic stuff? Take the mechanics from unidimensional, apply it to multidimensional, and call it good?
Why did you say that it doesn't matter whether the output is transposed or not?
In unidimensional case, doesn't,
Yeah,
because
for-
transposing a unidimensional variable, like a number, 7, transposes 7.
Yeah. But for a vector. not
For a vector, obviously matters. So the actual equation works like that. We don't put the transposes when we work with basic variables that are unidimensional because it makes no difference. When you don't say x, when you say x is a real number, you don't say x transpose because it's x. But when you do multidimensional, you have to put a transpose because the vector transpose, it's a very different vector. I mean, the same elements, just in the other direction. We have any questions here?
Could you repeat what exactly is happening in the second term of the differential? Like, how
Here?
are you? Yeah, this one. How are you taking?
How I got from here to here?
Yes, yes.
So I applied the first rule, right? It's W transpose times something, 2xt, da da da.
Right.
The first rule said the differential is that something.
Okay.
So it's everything except the W.
Right, but
There's 2x transpose y, 2x transpose y. The 1/2 comes from
Yeah.
the 1/2 in the front.
But W is a. I know you said the same thing. W is not a scalar here. I mean, are we just-
Exactly. So what happened here? I'm trying to cheat out.
Okay.
To be like, okay, to say, I hope my students trust me and don't notice that my math is kind of weird. Like, you take the scalar differentials, which I hope we all agreed on. This is the kind of thing that you shouldn't wait even a few hours. You should go right now. If you don't understand how the scalar differential works, you got to figure that out very quickly by like 3 p.m., okay? But how did Virgil, that's me, took these differentials, scalar differentials, and out of the sudden apply them to vectors? Like, maybe that's true, right? But we don't know why that's true. Did you see? I'm sure in high school you've seen the proofs of this. Why is this differential A? L'Hopital rule, limits, and all that, and you got to the A, right? But why is it true for vectors? I think that's your question. How did you take that procedure? This gives the whole proof of differentials, just puts the result. The result is that one, right? And I took that mechanic without any proof and I applied it to vectors. All right? Let me keep going with this. I'll get back to this. Yes?
I think I worked out how to do the second part. You just transpose the whole term. Like, you transpose it and WT in the front becomes WT in the back, so
Right.
you can do that.
What he's saying is that he believes me because he did the math in his head and it checks out, right?
Yeah.
Do you believe me that this actually works?
I believe him and he believes you, that's just that
So here's the thing. I want to solve this finally because I want to get to an answer and then I'll get back to how does vector differentials work, okay? What from here? We say this is 0, right? That's what we said from the beginning. We want to set the differential equals 0. So how do we solve this equation now? X transpose X W equals X transpose Y, right? Because 0 means equal, right? So what do we do? We multiply with the proper matrix inverse, we get W. So what do we have to multiply on? X transpose X inverse on the left side. In matrices, you have to specify whether you multiply on the left or on the right, because it's not the same. Like multiply on the right side, left side, is a different result. So now if I multiply this, it's done on purpose so that it cancels out this term, right? Because the matrix inverse times itself would be the identity. I get W is X transpose X at -1, that's what I multiply with, times X transpose times Y. What happened again? I multiply with the inverse of this matrix on the left side, so that the inverse times itself gives me the identity. I don't have to write identity, because identity multiplied with something is that something. And then multiply this on the left side of the inverse, I get that times whatever was here. Is that something I can actually compute? So this W, that's a solution for setting the differential to 0. I could take the X matrix, transpose it, multiply with itself, invert the matrix, multiply with X transpose, multiply with Y. That's the W's that this procedure says it gives the differential equals 0. And because it's a convex function, we have to solve that by Thursday. If this is a convex function, when's the differential going to be 0? In the global minimum. So for convex functions, we don't have to worry that there's other minimums or maximum. If we know it's convex and we got the exact solution out, that's guaranteed to be the minimum. But there's quite a few ifs in here. Is this convex? Did the vector differentials work? And the last step, that's a big if. If you can actually do this calculation, so you're going to see how even for small data sets, the one for homework 1, doing this calculation is not that easy because of this inverse here. X transpose, it's a matrix, a toy matrix, right? It's 50 features times 400 data points. But it's not a 3 by 3. It's 50 by 4,000. Then the other one is also 50 by 4,000, right? Do this, and we get a 50 by 50 matrix or so. Inverting that, it's an unstable operation. You can do it, but you have to be careful how to do it. For this inversion, you shouldn't try to implement matrix inversion by yourself. You should use some smart inversion, Java package, Python package, MATLAB. Pseudo inversion is the one that works best. Because the actual inversion, mathematically correct, is actually very unstable operation. And then I have to multiply this and get out. Now I want to get back to this point. We have 1 minute left here. There are 3 levels of machine learning in here. The first level is I want to do the minimum for the homework to get the bare minimum A in this class. You don't have to know this. I'm not going to require this derivation. Even this one, which is kind of shaky at the end with those vectors, this is not required for the minimum machine learning class. You are required to know the principle. I got differential, I differentiate it, I set to 0, I get that. This is called the equation formula, exact formula. You have to know where this is coming from, but I'm not requiring the derivation. The second level of machine learning is understanding the mechanics of it, even though at the end we had this step of, okay, well, you use that scalar into the vectors. You cheated me here, but I kind of believe you. At least I know how to differentiate things based on the scalar mechanics. And the third level of machine learning is the one that actually, okay, how do we do it for vectors for real? That's in the notes. It uses an operator for matrices called trace, and I'm going to spend 15 minutes Thursdays doing it for real, for the people who are purely mathematically oriented. Like, you're never going to use that unless you do a PhD in machine learning. You know, it's a pure math. We're going to do it for the, you know, historical, you know, archival purposes. But then you can trust me that this works for now. If I were you, I would set up for the middle level. Hey, there's some mechanics here that works out, and some mathematicians can figure this out for me. But we're going to do in class how this works for vectors exactly. We're going to get, of course, the same exact result, because this is true. This is correct. Now, the irony of all is that this method is totally infeasible in reality. Nobody would compute the regression coefficients this way because of the inverse. You may try to do it for the span-based data set, but if you go to any real data set, this is impractical. So we're going to use a different optimization method that's going to give us an approximate W. Not, this is the best W guaranteed, assuming he proves the convexity. Right? But in reality, we can't use this method anyway. We're going to settle for some approximate W that we can actually compute, because we can't do the inverse there anyway. So while this is an exact solution, it doesn't help us in practice. We need to study a different optimization method that goes little by little, and we hope that little by little it's close enough to the minimum. All right. I think it's better